Hey, a very warm welcome everyone. Before we start off about talking about the Mitsunobu reaction, I just want to clear out a few things. First, this video is divided into two sections, and those sections you will find down in the timeline of the video. One is for the basic learners and one is for a little advanced learners who want to know more about the Mitsunobu reaction, right? So depending upon your understanding of Mitsunobu reaction, you can skip to the relevant part. And one more thing is that you should also understand that this video is good from for students who are looking for a basic, like I said, a basic understanding of Mitsunobu reaction, either for your coursework, for your classes in the university, or either for competitive examinations. Mitsunobu reaction is a very important reaction, synthetic reaction, and a book can be written about it. So there are multitude of modifications that can come with Mitsunobu reaction. So it is not possible to cover each and every one of them. You have to understand this basic limitation of the video, right? So anyway, let's start off. What exactly is Mitsunobu reaction? So just a basic idea, basic understanding. So if we have an alcohol, now generally for Mitsunobu reactions, we have primary and secondary alcohols. And I will talk about a bit later when in what cases we can have tertiary alcohols as well. So basically, let's see a simple transformation that if we have a primary alcohol, and to this primary alcohol we add a very popular combination of something which is called triphenyl phosphine and DEAD. Okay, so this DEAD, what exactly it is and what is its structure, I'll just talk about in a bit. So if we add triphenyl phosphine and DEAD, this combination, and along with that we add a nucleophile. Okay, so I hope that all of you are aware of what exactly is a nucleophile. But this nucleophile, one characteristic feature of this nucleophile is that it should be acidic. What is the reason behind that? We will see a bit later in the video. So if you have a nucleophile and if you have this very popular combination, whenever you see this combination either in your a competitive exam or in your university exam, immediately it should strike to you it might be something to do with Mitsunobu reaction, particularly if there is an alcohol as well. Okay, so this will give us basically this is like a transformation that directly from the alcohol you get a nucleophile attached to this R group. So this R group can be anything. Right now I'm considering it to be an alkyl group, right? So for example, just as an example, so that you can visualize it well, if we have, let's say, CH3CH2OH, just a hypothetical example, and let's say to this we add this combination of triphenyl phosphine along with DEAD, right? And let's say in this case our acidic nucleophile is let's say acetic acid. Okay, just as an example, CH3 C double bond OH. Then what you should get is that this hydrogen will get removed in the reaction. So basically you will have CH3, CH2, and now this oxygen will be attached over here, O, C double bond O, and then you have CH3. Okay, so this is going to be your product. So you can see this nucleophile has replaced the alcohol over here. Okay, don't get confused. This oxygen completely gets removed. Okay, so this whole group basically gets attached over here. So from an alcohol we end up having an ester. So that is basically one example of Mitsunobu reaction. Whatever nucleophile you might have over here. Now you might also have a thiol over here, for example. So this thiol, then this sulfur will get attached over here. So in this case you will get the product as CH3, CH2, CH3. So now I hope you can understand that why it is such a important and useful transformation. Now let's try and understand the mechanism of how exactly it works. Okay. Before we understand the mechanism, let's talk about DEAD. Okay, so DEAD is nothing but azo compound. So azo compounds you might have heard about. This is basically the basic, you can say, core structure of an azo compound. And for DEAD we have two ester groups attached over here, CO2ET, CO2ET. So this is DEAD, basically stands for diethyl azodicarboxylate. Okay, that is the full form of DEAD. And azo compounds are, you might have seen used in organic dyes. They are very popular. You will see this particular functional group which is present in organic dyes. And DEAD is a very explosive compound. So if some of you get the chance in future to use it, make sure that you are very careful. These are highly explosive compounds. In fact, their transportation is not done in its pure form. It's done definitely in a diluted form, like maybe it is mixed with toluene or some other solvent so that it gets diluted, right? So in pure form it is highly explosive compound and you need to be very careful. It can explode, I think, above 100 degrees Celsius if you heat it to 100 degrees Celsius. So you need to be very careful when you're handling DEAD in the pure form. Anyway, that's just a precautionary measure that you should keep in mind, and nothing important from a theoretical perspective. Anyhow, so we have this is a diethyl azodicarboxylate. Now we have triphenyl phosphine. So what this triphenyl phosphine does is it has lone pair of electrons, and this pi bond is very weak. Okay, this N double bond, and this pi bond over here is very weak. So these lone pair of electrons attack this nitrogen over here, and these electrons, pi electrons, migrate to this nitrogen. Okay, so what do we have? We have N double, next step. Okay, just follow the steps. So we have N minus over here, then we have CO2 ET, and you can understand that this what do you call this N minus over here, the anion basically that is being stabilized by conjugation with the ester, right? So then we have your CO2 ET over here, just like that, and we have this triphenyl phosphine group attached. Now this N minus over here, what it exactly does is, you can think of it in two ways. So you have alcohol, right? You have your alcohol, which is the starting material. So you can show that this alcohol over here, this basically goes and attacks this phosphorus, because oxygen has a very strong affinity towards phosphorus. And at the same time, this N minus basically abstracts this hydrogen. Because when this oxygen lone pair will attack this phosphorus, okay, when they will form a bond, so this oxygen will have 3 bonds. So that is why it is going to have a positive charge over here. So then this N minus can abstract the hydrogen. So I'm just skipping this step. What I'm going to be showing you is this N minus is going to abstract the hydrogen of this particular alcohol, okay, that we have as a starting material. So over here I'll just show it as NH. And at the same time, I will just show that this oxygen goes and attaches to the phosphorus, okay. So when this, or I just show it as O minus, and then this goes and attacks the phosphorus. So when this one goes and attacks the phosphorus, this bond breaks off. So now what do we have? We have PPH3 attached to the oxygen. Oxygen has a very strong affinity, so this is our alcohol basically, right? This over here is our alcohol which is attached to the phosphorus. And now we have N minus NH, right? CO2 ET. So this is our diethyl azodicarboxylate, okay? And then we have N minus over here. Now what happens is this N minus will abstract the hydrogen of the nucleophile. And now this is where the importance of the acidic nucleophile comes, because this N minus over here wants the proton of the nucleophile. So let's say if we have an acid, let us take a R dash C double bond OH, right? So this hydrogen over here is highly acidic. So this N minus would like to abstract this hydrogen over here, right? This N minus over here would like to abstract this hydrogen over here. And since this is an acidic hydrogen, it can easily do that. But the problem is, if we have some basic nucleophiles, by basic nucleophiles, you can consider, like for example, RNH2, okay, any amine, or you could also consider nitrile or alkyne, like C double bond CH, okay, or you could also, take nitrile group. So these are some, like the basic nucleophile, you can consider this over here. Now the problem is that this N minus will have difficulty abstracting the hydrogen over here, because this is not an acidic hydrogen. And because of that, what is going to happen is, like, let me just draw it as OCH2R group. What is going to happen? This is a very important thing. The side product is that this N minus over here can go and attack this carbon. And what is going to happen is this N minus over here, or this DEAD compound, the reagent will get alkylated. Okay, so alkylation basically is going and attacking an alkyl group. This bond will come off. So this will come out as triphenyl phosphine oxide. So this over here is going to come off as triphenyl phosphine oxide, and this whole group over here will get trashed to this our reagent, that is DEAD. That is the big issue. That is why over here we need acidic nucleophile, so that this N minus over here does not show this side reaction, does not get alkylated. Okay, so if this side reaction is not happening, then what is going to actually happen is that this N minus over here is going to abstract the proton over here, and this is one of our products. Okay, this over here is one of our products, right? The other product is that now we have this as a good nucleophile, and now this O minus over here goes and attacks this carbon. Okay, so you can show it like this. It attacks, and now your triphenyl phosphine oxide is removed as a byproduct. Okay, so now we have this R CH2. Now the oxygen is attached on this C double bond O, and this is R dash. Okay, so this over here is our nucleophile that is attached, you can see, and the alcohol over here is removed, and the byproducts are triphenyl phosphine oxide along with this compound. So this is a Mitsunobu reaction. Sorry for the very messy presentation, but I hope you have been able to follow. I've tried to go as slow as possible, right? So this is how this reaction looks like. Now, a few important things, even for basic learners, that you need to understand about Mitsunobu reaction is that what about the stereochemistry? So if you have primary alcohol, we do not need to worry about the stereochemistry. But if you have secondary alcohol, so what is going to happen if you look at this step over here that we had? Okay, let's redo the mechanism so that we can understand it much more better, and it can somehow get mapped in your mind as well, right? So let's quickly do a mechanism with a stereocenter present. So we have R. Let's say we have a secondary alcohol, and let's say this alcohol is above the plane. Okay, and then we have some, let's say, like ethyl group. Okay, so we have ethyl group, right? Let's do the transformation again. So if you remember what is going to happen, first thing is we are adding diethyl. This reaction is going to happen, DED and triphenyl phosphine oxide together. It will form N minus. This N minus is going to, let's say, this oxygen over here is going to attach to the phosphorus. Okay, so I'll just show it to you over here quickly. So this oxygen over here goes and attaches to the phosphorus. We can remove this hydrogen over here. So it is attached to PPH3, and along with that we have NH. One of the groups get protonated. We have N minus, and we have CO2 ET. Right? Now what is going to happen? This N minus, whatever our nucleophile is, let's say, again in this case, let's consider an acid. So we have, let's say, R dash, C double bond O minus. Okay, OH actually, first it will be an acid, then this N minus is going to abstract that, so it will form O minus, and this will get protonated again. This will form NH over here. Now this O minus is what it's going to do. It is going to show an attack. It is going to be an SN2 reaction basically, right? So there is going to be an inversion of the stereochemistry. This group will come off as triphenyl phosphine oxide as a byproduct, and what we are going to have is this ester now that is formed is below the plane. We have R dash, we have ET. So you can see there's an inversion of configuration. So there are two important things that you need to understand. First is that this is, again, like you can say, the nucleophile has to be acidic in nature. You cannot use basic nucleophiles. Now, of course, there are certain modifications to the Mitsunobu reaction due to which one can use basic nucleophiles also, but we are not going into the modifications. If you talk about the basic Mitsunobu reaction, one of the limitations is that you cannot use basic nucleophiles, you have to use acidic nucleophiles. Now you know the reason behind that, right? So roughly it is said that the pKa of the group of the nucleophile has to be around 12. Okay, roughly the pKa of the nucleophile, okay, the acidity of the nucleophile has to be around 12. And if it is more than 12, generally the Mitsunobu reaction is very sluggish. It does not proceed as required, right? So that is why acidic nucleophile is one of the most important things, and that you need to keep in mind. If someone really wants to test your understanding of Mitsunobu reaction, this is one question they could definitely pose to you. The second is that there is an inversion of configuration. This is again a second very important part of Mitsunobu reaction. It's a fundamental name reaction, a very good synthetic transformation for converting directly from alcohols to, for example, let's say esters. And one more utility I would like to tell you about this, that why this inversion is important. Because let's say, okay, let's take an example wherein you want to do a certain transformation. Let's say you want to make an ester and you have a stereochemical center present over there. Okay, so let's take an example wherein you have let's say CH3, let's say R group, okay, and then there's a stereo center over here, let's say methyl, and then you have OH, okay, and one thing is that let's say you want to convert this into a corresponding ester. So what you could do is you can react it with, let's say, CH3 acyl chloride, okay, you can react it with acyl chloride, and over here what is going to happen when you react it with acyl chloride? You will have R. So this will remain above the plane O. COCH3. Right, so this is a simple transformation that you can have an acyl chloride. And acyl chloride, you know, can be easily synthesized from acids, right? But the problem is that if you want this CO center to also change, you want the ester, but at the same time you want the CO center to change, this is where Mitsunobu reaction can be very useful. So what you could do instead is you could use this reagent itself. Okay, you could use this starting material itself, right? Same starting material, and you can use the same acid. So instead of like from the acid you will form the acyl chloride, instead of that you can directly use that acid. So let's say we directly use CH3COOH. Okay, so this is going to be a nucleophile of the Mitsunobu reaction, and then of course you add your triphenyl, phosphine, and your DEAD. So what is going to happen is this is going to attack at this particular carbon. So the stereochemistry over here is going to invert. So what you will get in this case is also this reagent, this ester only, but you will get the other enantiomer. So over here this will go below the. This is again a very strong utility of the Mitsunobu reaction, right? So from the same starting materials, roughly the same starting materials, because like I said, this is acyl chloride, you can synthesize from the corresponding acid that we are going to be using over here. So what you've actually done is that you have in one case you have retained the stereochemistry, and in the other case you have managed to invert the stereochemistry in one particular transformation. So this is a very, very strong utility of the Mitsunobu reaction. Now the next thing I want to talk about is tertiary alcohol. We generally don't see Mitsunobu reaction being used for tertiary alcohols, and one of the major reasons is steric hindrance. Because if you look at the mechanism, in this mechanism, if you remember, the alcohol over here, the oxygen, basically goes and attacks the phosphorus. Okay, and the phosphorus, you can say ligand that is generally used over here is the triphenyl phosphine. Now, as you can see, 3 phenyl groups attached to the phosphorus, it itself is bulky. So primary alcohols and secondary alcohols do not have much difficulty in approaching this phosphorus. But when you talk about tertiary alcohols, they will have a lot of difficulty. So due to these steric hindrance or steric issues, you can sort of like understand that why tertiary alcohols might not react really well in Mitsunobu reactions. Yes, that if you use phosphorus-based ligands which do not have phosphorus, like your phenyl group, maybe which has smaller groups, like for example PME3, like 3 methyl groups attached. In that case, you can utilize Mitsunobu reaction for even tertiary alcohols, and there have been research reports of Mitsunobu reaction proceeding with tertiary alcohols also, but generally it is not done, and you can understand the reason behind that is more majorly steric reasons, right? Okay, so let's look at some applications of Mitsunobu reaction in reaction so that you can understand it much more better.
Okay, so these are some of the important transformations according to me which have some relevance. I have taken them from a couple of good publications, some of these examples, and of course from G. Jackley, a name reactions book, and most of the video that I had made also had a lot of contribution or a lot of knowledge transfer from Claydon. Anyway, so this is the first example. So like I mentioned to you that the pKa value or the nucleophile has to be sufficiently acidic. So this is a very good example of a Mitsunobu reaction wherein the nucleophile is a carbon, acidic carbon. So you can see the pKa of this particular compound is around 7.5. This is actually a trimethyl carboxylate, and this CH proton, as you can see, this is quite acidic because it will be in conjugation, or it will be stabilized by these 3 ester groups. So you can see this transformation goes in high yield, around 88%. And secondly, like I told you, there's the inversion of configuration. You can see that the stereochemistry has been inverted, and this group is now above the plane. The alcohol was below the plane. So this is a very good depiction of whatever we have just studied a few minutes back. Then this is another a straightforward transformation. As you can see, there's a acid, so this acid is going to act as an acidic nucleophile. Again, over here you can see alcohol is below the plane, so there's an inversion of configuration, and you can see that this acid along with this aryl group, right, has been attached to the position where the alcohol was there. So this is also a very good example of the transformation that we just studied. And over here, these two examples are something that I really wanted to highlight so that you don't get confused. Now, if you remember that I told you that the amines generally, because of their high pKa values, they do not really they end up acting as basic nucleophiles. But if you see over here, this NH, this is acidic in nature because it is in conjugation with this a double bond over here, right? And along with that, it is also in conjugation with this tosyl group. So this NH over here turns out to be quite acidic in nature, and that is why you can see this transformation is also possible. And this is another example. Some of you do not know what exactly are these tosyl groups and this nosyl group. This is an important reaction. This is an intramolecular Mitsunobu reaction. So this nosyl group is what I have depicted over here, right? This is I think this is the nosyl group, and as you can see, actually this is nosyl chloride, not the nosyl group. So if we write NHNS, that means this chloride has been replaced by nitrogen. Okay, so instead of this chloride over here, this is an example of nosyl chloride. Okay, so over here this chloride basically has been replaced by NH group. Okay, so here we'll have NH and then the corresponding this whole particular functional group, like this whole particular molecule will be there, but instead of this Cl we will have NH. So now you can understand that this NH is also highly acidic. In fact, if you think about it, sulfonamides, okay, SO2NH2, sulfonamides are also acidic nucleophiles, because even there the NH proton becomes acidic because it is in conjugation with the sulfoxide group. Okay, so that is why over here also we can see that there's a primary alcohol present, and there's an intramolecular, you can see Mitsunobu reaction where this nitrogen replaces the alcohol. So this NH or nosyl group basically acts as our acidic nucleophile. So this NH proton becomes highly acidic, like I said, because of the conjugation to the sulfoxide group, and that is why it is able to show this intramolecular Mitsunobu reaction. So these are some of the examples that I thought were important, I really sincerely hope that you learned something new from this video. If you like these kind of videos, please do give it a big thumbs up so that I get to know that these are some of the videos that you would want to see, and you want to have detailed videos, because initially I was quite skeptical of uploading this video because it's around 20-25 minutes, and I was not sure whether you want shorter videos which just give you a basic idea, or do you want videos which give you a good depth and in detail of these name reactions. So if that is something that you really want, do let me know in the comment section so that I'm encouraged to make these detailed videos, because honestly it takes a lot of time. I mean, making basic videos is quite simple, quite straightforward, but getting these examples, collating these examples and then presenting it to you takes a lot of effort. So I would really appreciate if you can leave a comment down below of what exactly or what kind of videos that you want to see with respect to name reactions, whether they should be absolutely basic to the point, or do you want to go more into the depth and details of the name reaction. So yeah, thank you so much for watching. I'll see you in the next video very soon. Hey guys, so I'm a verified educator on Unacademy, and along with that I'm also available on the Unacademy Plus platform, where I'm taking live classes along with other educators. So in case you're interested in attending the live classes, you can subscribe to the Unacademy Plus platform using my referral code, that is SETHI, and that will give you 10% discount. Alright, and in case you're not interested in attending the live classes, you can watch the free courses that are available on the Unacademy. For that, all you need to do is go to the Unacademy website or download the Unacademy learning app and search my name over there, that is SETHI. Once you do that, you will get the access to all the free courses that are available on the Unacademy platform. Alright.